Hi everyone, I'm happy to present this day's evening and whatever time it is on your side, episode of AI Suisse again. Happy to have you here and to welcome Ashish. Happy. Hi.
Hello, hi.
It's fantastic that you found some time to speak today because I think this subject we have today is quite interesting from many angles.
Yeah, definitely. Thank you for having me here, and I am looking forward to share, some of the things that I've been thinking about. I mean, this is a very important topic, and I do believe that we can make a significant difference.
Yeah, I'm sure as well because I think also you're quite have a lot of expertise in that area. You're flying yourself, right?
Yes, indeed. I am an avid aviator, and I live and breathe anything that flies. And one of the reality is that flying is very expensive, not just from the money perspective, but also from the environmental currency perspective that we are using. And consequently, it's a yes, I do fly a lot, and I do think about these things a lot.
So it's, as you say, it's thinking about if flying makes so much fun, can it be also more environmental friendly, right?
Yes. Absolutely. I mean, if you think about a history of transportation, for thousands of years, a man, lived and died within few miles of a spot.
Yeah.
And it was not until advent of transportation and really, advent of flying machines that we are able to span such geographical distances. And so it's amazing what we have accomplished, but it's also very expensive. So yes, indeed.
From your job perspective, just to have a look at it for a second, you're managing director for the Autonomous Systems Research Group at Microsoft. So what is the research you're doing?
Yes. So my background is machine learning. When I finished my PhD, that was long ages ago. I was thinking a lot about data. I was thinking about Bayesian inferences, and at that time, machine learning was still in infancy. So in the sense that all you could do with machine learning is maybe output some labels. You can recognize some handwritten digits and things like those. Our ability to act on machine learning decisions have greatly been enhanced in the last decade. With cyber physical systems, with robotics, now you can actually take all this pattern matching and machine learning, machine intelligence capabilities that we have developed, and you can change the world. You can physically react in it, and that kind of gravitated me towards robotics a little bit. And of course, given my personal passion in flying, aerial robotics was a very natural place. So we started a research effort within Microsoft Research around aerial robotics. And one thing that I believed in, and I continually push, is the role of machine intelligence in in aerial robotics. Um, not only from the perspective of doing drone deliveries and things like that, but I also realized that how stressed our aerial transportation system is. So if you're a pilot and if you're flying, that the frequencies are clogged. We are essentially relying on World War II infrastructure in for our modern needs, in order to scale up, in order to make this transportation more efficient, accessible, as well as energy conscious. We will have to rely on machine intelligence techniques. So that's what my research group at Microsoft Research focuses on, thinking about aerial autonomy with machine intelligence and machine learning at the center of it, in order to bring out changes which are positive towards the society. Right. So that's the goal of the research group, and we are looking forward to see how we can change things positively.
That's a good thing, especially since we have a climate change talk for some time now, and everyone is just like thinking about what can we do to save the planet in some ways, right?
Yep.
It's
Definitely.
awesome to have you here. Just a quick welcome again for everyone who joined us. Happy to have you here. A quick organizational note, as you've seen in the navigation bar, there's a Q&A section where you can actually place your questions if you have questions during the talk. please feel free to ask them. There's no silly question, as you know. And Ashish and I will take care, especially I will take care to read your questions and ask him, even if he's talking. So as usually, don't wait until the end. We can ask questions throughout the presentation because we want to have more like a conversational style. So happy again. Ashish, I told you already, but I'm really looking forward to your talk today. And I found it interesting because I personally was always attracted by thinking about how can we learn from nature how to get better with things.
Yeah, no, absolutely. It's interesting that when you think of all these birds that would migrate greater continental distances, and they are doing at a fraction of energy that we use to fly airplanes. And so there is something about intelligence, there is something about decision making, something about harnessing the power of nature so that you can accomplish your missions while being very conservative and very thoughtful about the environment.
Interesting. So I just take the floor and show us what you want about your
All right. Sounds great. Thank you, everyone. So thank you for having me here. And, I am excited to talk about, I would say it's one of my favorite topics. This line of work really is thinking about how to help reduce environmental impact of aviation, specifically with machine intelligence. What you see at the bottom of the screen is a snapshot of air traffic at a given moment of time. I think it's somewhere in 2019. So this is pre-COVID. But I would still imagine the levels of traffics are similar. We see a lot of traffics at a given moment of time, somewhere around 10,000 to 20,000, depending upon, night or day and things like those. This is I would say, the blood of the global economy, the transportation, our ability to move things around, ability to move people around, our ability to move ideas around. It's a very important component, and we got to rely on it, but we also understand that this is coming at a very at a great cost. So here are a few of the thoughts, few of the research works that we have tried to address some of these these concerns. My background, as I mentioned to Stephen, like I'm a machine learning researcher, and have been doing robotics since 2014, mostly aerial robotics. But on the other side, I'm also plugged into the aviation community very closely. I'm a flight instructor myself. I care about not only the health of our planet, but also the health of our ability to transport, to move goods around very efficiently. I originally come from India, and I always, longed to go back home. And I think that's what my connection to aviation has been, because it's a promise that you can actually travel great distances very rapidly. And so there is a lot of emotional energy invested into some of the things that I'm going to talk about next. Right. So, yeah.
Just show me the animation once more. Can you start it again?
Yeah, absolutely. Absolutely.
Guys, because sorry that I interrupt here, but this is so interesting to see really the hotspots on the world map. And this is just like there's so many areas where I can see no planes. Very dense areas.
Very dense areas. I think if you look at primarily Europe and primarily North America, this bulk of the air traffic is happening. And as you can imagine, places in Africa where the population density is very less, near Sahara Desert, for instance, it's hardly any planes there. Also at the other parts of the world, Tibetan plateau is, for instance, talked about. But yeah, the density is uneven, but still it's dense. And as you can imagine, that we talk about eVTOLs, or what they call flying cars colloquially, or drone deliveries. This thing is going to just explode. The potential is huge in terms of our transportation needs. So one of the statistics that I read from a report like long time ago was, so right now to travel, for instance, within Delhi, a distance of 5 miles, it might take you a couple of hours. Imagine if there was local air transportation from building to building, that distance should be less than a few minutes. Our ability to scale up transportation from 2D to 3D has immense immense consequences. And I think we have to be mindful about the benefits, but also how would we appropriately scale them up.
Interesting.
Right. Okay. All right. So I'll continue. And as Stephen said, please ask questions. This is great as a discussion. Again, this is a formal presentation, but what I believe, in order to make efficiency possible in aviation domain, there are two things that you could do. Right. One is predict your weather better. Right. If I know what the winds are doing, I can possibly ride on it. And I think birds and other migratory creatures do that extremely well. They have a very keen sense, keen awareness with the nature, and they'll ride on it. And of course, we can take better decisions. If we know what the winds are doing, we can actually utilize them. And I'll give you an example. Right. So first, let's talk about what's the environmental impact of aviation that's happening. And of course, I started this as a young, naive boy enamored by airplanes, but it was not until later in my life that I started realizing like these things are very expensive. So just to give you a sense, the emissions are harmful. You are getting carbon dioxide, carbon monoxide, hydrocarbons, nitrogen oxides, and all the kinds of chemicals that will be harmful. Lead is one of the big hot spots in general aviations right now. So all the small airplanes that you see, they do have lead in the fuel, and this is probably one of the only vehicles right now that needs lead. And the reason is the engines that we're using in these planes were designed 40, 50 years ago, and they need lead as a lubricant. While we know that there are harmful properties for lead, unfortunately, there are no good alternatives. So, there is a lot of debate around this topic. We do know that these general aviation small aircrafts are lifeline for many rural communities across the world. So it's not that you can just shut them down, but also the reality is they do use lead in those fuels. So consequently, I think we need to figure out a balance. I think some of the best minds are working at it. And just to give you a sense of what kind of difficult questions that we are dealing with. The second thing is, in 2017, this is again, as I said, right, some of this work is dated in 2017. Aviation resulted in 859 millitons of carbon dioxide. That's 2% of man-made carbon emissions. And I mean, 2% is a significant bit. And so there is definitely something we could do. But one of the statistics that blows my mind is the following, right? One round trip of transatlantic flight can melt 30 feet square of Arctic ice. That's one round trip.
For a second, I had to look up what 30 square feet are actually in meters, in square meters. It's about 2.7 square meters. So this is just one flight, as you say, right?
That's one flight. That's one flight. And imagine like how many thousands of flights across.
Yes.
And over the years, so there is a huge environmental impact, right? And of course, there have been talks and people have been cognizant about it, but they have not been easy answers. So just to give you a sense of, this is there is a lot we can do here. Okay, so moving forward, right? What is the basic? I'm a technologist, right? I'm a technologist. Of course, there is a lot of work that we can do in policy making, but from the technology point of view, what could we do, right? Let's assume a theoretical question. Imagine you got to go from a start to an end point, and there is a big wind vortex. So these are probably maps you've seen. Most of the wind structure in the environment are like these. These are gigantic structures with circles and troughs and at high altitudes, at the altitudes where these airplanes are flying, you can see winds up to 200 miles an hour, right? So you can see that poor flight can result in very long flight times, poor flight plans. But something that's efficient, you can actually, ride on it. In fact, when you are learning, and a lot of pilots forget this lesson, is that when you're traveling across the continents, depending upon low pressure or high pressure, your route should be going more northerly or more southerly. so that you can actually use the winds. But of course, we don't have tools. Our weather prediction, the wind predictions are still very poor, as I'll give you some examples. So again, conceptually, you have a start point and you have an end point, and you have some kind of vortices. The question that I'm asking is, what's the most efficient route, right? And if we can even do that, I think the promises, the promise is enough. Like, promises a lot, actually. So the problem, I mean, this is a chicken and egg problem. The first problem is that we don't usually have accurate predictions, not uniformly across the entire globe. Sure, there might be places at the globe where you know really well what's going on, but there might be other places, especially where you're doing long distance flights, where you might not have enough information, right? And so it becomes, theoretically, a decision making under uncertainty problem. You want to utilize the winds, you don't know the winds, and you don't know the winds. Then how do you plan, or what kind of policies can you employ? So that's the crux of the problem that we want to look into it, right? So there are two key ideas, as I said: better wind forecast. You do better at providing forecast, or you do better routing, either of the two. And here I'll talk about both, right? How to do better wind forecast, and specifically piggyback on already what we know, because there are 10,000 airplanes up in the sky. You have a lot of information sensors, and you can harness those out. And the second thing is better routing. So, this is again an anecdote. So there is an Air India flight that goes from Delhi to San Francisco, and it's 16-hour flight. It's one of the longest flights out there. And a couple of years ago, there was a team of flight planners that worked very hard at it, and they were able to shave off a couple of hours for that season. And a couple of hours of a transatlantic flight carrying 300 passengers is huge. That's every day.
Yeah.
Right. So this is just with one flight. So imagine if you could scale this up, if you could do this for every single flight in the world that's going on, we could really have a very positive impact, right? So those are the two aspects that we're going to talk about, right? So Stephen, any questions or any thoughts?
Question, but maybe better for this one, better for the end.
Okay. All right. Sounds good. All right. So let's think about better wind prediction. So as I said, like, this is a snapshot again. This is from a service called Flight Radar 24. If you just go right now on your browser, flightradar24.com, it'll give you similar maps. And, these airplanes, they are basically up in the sky. And right now, I think on this snapshot, there were 10,000 of those. But yeah, there's a lot of air traffic up there. The thing is that this airplane is experiencing wind as it's flying. And if we have mechanisms to aggregate that information and beam down, we can actually get a real-time wind model, which is very accurate, that which other and future flights can piggyback on. That's the basic idea, right? So your airplanes aloft are a sensor network, and you could utilize all the information that they are experiencing to come up with better weather models. And again, mind you, this is not an idea that I had thought about. People had thought about it. It was essentially using, it was called an AMDAR effort within US, where they had instrumented, and they had, they had, for the participating airlines, they had all the infrastructure so that they can beam things down. And even the airliners on their local part, they try to do that. So for instance, if you have, Air France or Delta flights going, there are people who would aggregate the information by hand or by some computer means or things like those, and try to broadcast to their team. But it's happening at a very local level, right? Unless you are a participating airline, which has the appropriate sensing authority, right? Or you are part of some within airline program, like, this information is not being aggregated, used. So what I'm going to show you is basically a machine learning technique where you don't need any airline approval, any government approval, any infrastructure, right? It's just completely simple mathematical trick. And you can actually aggregate all this information, right? So it's very, very easy. You could probably code it up on your laptop in, few hours. It's as simple. And what it's relying on? It's relying on an information feed. So basically, all these airplanes are broadcasting their GPS location, their intent, their flight plans. So even if let me see if I have that. Well, I'll come back to it. If you're on the flight radar 24.com, and if you just hover over one of the airplanes, you'll see this information that, all right, going at this speed, this is the ground speed, flight plan from New York to Seattle, all that kind. This is publicly available information. It's delayed for us by 5 minutes. Like, unless you're an airline, you don't have a real-time feed. But if you're not, you have, it's a little bit delayed, but big deal, few minutes, right? And it's all out there. And intuitively, here's what I'm doing, right? Imagine I'm today flying from Seattle to New York. And today, instead of 6 hours, which is the normal time, I'm able to travel that in 5.5 hours, right? So this is a signal from my machine learning algorithm. All right, the winds are helping this guy out, right? So that's it. You take that bit of information, integrate it across the entire sky, and what you have is a very sophisticated wind model, right? So again, just going into the basics of it, it's using vector algebra. So people who are doing machine learning are familiar with this. Is what you were taught in high school. Airplane is facing a heading with an airspeed, so that's the red arrow. And the wind is the blue arrow. And when the heading meets the wind, it changes your ground track and ground speed, which is the green arrow, right? This is the vector algebra. If I know the red arrow and the green arrow, I can reason about the blue arrow, right? That's simply what's going on. Of course, because our architects who design these kinds of systems didn't think that people would want to compute wind velocities. It turns out that getting information about the green arrow and the red arrow might not be straightforward. So let me just get a little bit into it, right? So for instance, if I just hover over an aircraft, so for instance, here is this, American Airlines aircraft, right? Yeah. It gives me a few information. It gives me altitude, right? So this is at 37,000 feet, right? Its ground speed is 500 knots. Right, so it's going at 500 knots, and it's a track 125 degrees. It's going. There's a latitude and longitude, right? So we have some information. So the information we have is basically the green arrow. We have the heading and we have the velocity here, right? So we have the full information about the green arrow. So now, if we have information about the red arrow, I think we are home free, right? But it turns out we don't have all the information about the red arrow. Of course, we don't have the wind velocities. You would imagine that in modern days, like if we design again this kind of a communication system, wind velocity is something that the airplane can compute locally with its GPS equipment, but it's not been broadcasted for some reason. I mean, it probably because of the design, the legacy design. So our hope is that let's find out what the red arrow is. The red arrow is also not there, and but there is a little bit something that we can take care of. If it's an ill-defined problem, you only have green arrow, but you don't have red or the blue arrow. And how can our machine learning help you do this? So the first thing is that, if you dig a little bit deeper, you have a little bit more information. And what information do you have? You basically have, what they call the airspeed planning. So you have, say, this 505 knots is your ground speed, and you had planned for 452 knots. Right. And what that is, it's basically the magnitude of this arrow. So you don't have the actual direction, but what do? You got, what's the magnitude of this vector? Yeah. So it's a little bit better than nothing, right? We don't have the heading still, but at least we know that this guy wanted to go at 450 knots. Right now I'm saying 500 knots, but that was the original airspeed that they were planning, right? So the thing is, now this comes machine learning hammer. The machine learning hammer is the following, right? Sure, this triangle is ill-defined for one airplane, but I have 10,000 airplane up there, and I can use something called spatial smoothness. The intuition that two triangles that are closer to space should have similar red arrows, similar winds, so similar blue arrows. So that's an intuition, and that's an encoded in something called a Gaussian process prior. Again, this is I'm happy to send you the references, but intuitively what it's using is saying that nearby airplane should have the same blue arrow, and that information is good enough for us to now reason about, break this ill-defined problem and bring our mathematical, hammer. So this is basically a graphical model. This is, 6-7 years ago. This is before neural network became all, rage. So this is going from first principles still. We have a better model with neural networks now, but I wanted to just share the intuition of what it is, right?
Just
so
we have one question here regarding what you said about speed. Saudi is asking, how can we trust planned speed? Or do we already take into account wind speed when we plan the speed?
Yes. So that's a great question. So usually here's the deal. When you file a flight plan, you have to provide what airspeed that you're going to do. So what airspeed is basically imagine if your air mass was stationary, how fast you'll be going through that. That's your airspeed. So every single airplane has to provide its airspeed, what is called true airspeed, right? Yeah. And in case if something changes and if you deviate from that airspeed more than 10% of the time, you got to report it back. So sure, it might be noisy, but that noise is bounded and we understand what kind of noise that is, right? And again, it's the power of statistics. Sure, one of the observation is noisy, but you have 10,000 things up in the sky and you can actually, the signal, you can actually do the signal to noise analysis, ratio analysis, and you'll find that you have enough information even under noisy circumstances to circumvent, bad information.
Interesting. Since you've shown that kind of website before, but I posted the link to flightradar24.com in the chat for everyone who wants to just look at it, or if you know it already, it's fine. Did you use that to get the data?
No, I didn't use that to get the data. So the thing is, many of these sites, so FlightRadar24 is one website. Yeah. We have flightaware.com, and there are other providers as well, right? I'm using FlightRadar24 just to give you the depictions and the informations, right? Yeah. But what we do at Microsoft, we have, like as a business entity or as an individual owner, you can ask FAA, at least in US, and subscribe to the data feed.
Okay.
Right, and it's a public service. This data is all out there, right? And you can subscribe to that FAA feed, and you can get all this information. And of course, FlightAware and FlightRadar, they have their own software APIs as well. So you can pay them few cents per query, and you can build your thing over it. But FAA, at least in US, also have means of providing you that feed directly.
Yeah.
Yeah. Thank you. Right. Okay. All right. So, again, this is a graphical model. It's for folks who are technically, interested, what we have a W as a random variable, which is which depicts the entire wind field over the entire globe. And it has a Gaussian process prior, which is spatial smoothness, basically saying that, winds experienced by aircraft close to each other should be similar. So W is latent. We don't know. What we know is we have some wind station information. So every airport, for instance, will share what wind it's encountering. And we have these services that will kind of give you some sense of what the weather is at various stations. So, they are blue, shaded blue. That means that they are observed. And then you have aircraft observations for which you don't have the actual wind, but you have auxiliary variables, which are the velocities, the ground velocity, the green arrow that I was talking about. And then you crank on, Bayesian inference. In this case, what we're using is a Laplace approximation and basically reason about the entire wind field. The details are in the paper. You're welcome to look at it. But, I'll just move on, and I'll show you, some of the anecdotal evidence on why this makes sense, right? So again, how do you even test whether this algorithm that you came up with it makes sense, right? So, we do some proxy experiments to investigate this. So what I'm showing you is a winds aloft report from NOAA. NOAA is the weather agency in US, and this is they basically, this is the aviation weather, right? Every 6 hours it gets updated. And, one fine morning, this is what's happening, right? Again, this is a control. So let's not worry about this one. This is, some comparison that we're doing with some basic information. And if you use the scheme that I just mentioned, you are getting this kind of a wind field. So if you look again, both of them are northern westerly, right? But this one is going a little bit more north up. So this is a significant difference between what I think the aircrafts are seeing and what this model is predicting. And this is a systematic, error. It happens across the continent, right? And you can imagine, like, I mean, at the speeds that you're looking at, right, at 40,000 feet, around 100 to 200 miles an hour, right, the direction of arrows can make a lot of difference on how you're going to flight plan out, right? So again, this is just a highlight how much difference there can be once you start incorporating the the wind information. We did additional experiments, and this is we had a couple of high school students who were into launching weather balloons. So if you are familiar with what these weather balloons are, these are giant latex balloon that you put GPS and other sensors in, and you release those balloons. The balloons will fly. They will go almost up to 100,000 feet or 120,000 feet, and drift with the wind. And and at 120,000 feet, it'll rupture, and all the payload will come down, and you can go and collect it, and you can look at the GPS track and things like those. So we use one of those experiments to verify that our wind models are actually a little bit more refined than what at that time NOAA was doing. Right, so we've done some of those kinds of field experiments. Those are all detailed in the paper. But let me move on. Right. So Stephen, how are we doing on time?
That's perfect. Wonderful. Don't feel pressure.
Okay.
I'll let you know if something is going wrong, but this is absolutely beautiful.
Okay, sounds good. All right. So the second thing, I mean, this is one way. I think this is the scheme that I mentioned to you is very basic, right? It's very simple. All you go to do is just tap into all this weather information that exists out there, and you have suddenly much more refined winds, and more so in the areas where a lot of airplanes are flying. And I think you care about those anyway more, right? So at least there's that bit to it. And of course, for long distance flight, we still have the problem. We still don't have enough information. Specifically, if you're flying over the poles, over Africa, over regions where there's not air traffic information, possibly you don't have enough information to get better wind prediction maps. So better routing might be a way to do it, right? So let me explain what I think about it.
How can we improve that kind of measuring, sensing the wind, for example, the atmosphere? Is it a matter of using more satellites, or what is it? Is it more sensors in planes?
Yeah, so here is the deal, right? I think most of our weather reports are generated with remote sensing. Mm-hmm. What does remote sensing means? That these are images that satellites are taking, right? And but that is not enough. Yeah. Right. I mean, that's a proxy information. You are never directly measuring things. Yeah. So worldwide, a lot of weather modeling agencies launch these things called weather balloons. Mm-hmm. And this is very similar to the weather balloon that I just talked about. In US, I think the number is somewhere around 200, maybe a little bit less than 200. Right. So every morning and every evening they launch it. And sure, US is probably one of the most densest network of weather balloon, and that is not enough either, right? But there are regions in the world where this doesn't happen, so we have no information, right, virtually. And there is a reason that we are launching these weather balloons for now over 100 years, because that's the only way for us to directly measure these upper atmospheric phenomena. Right. And our lack of such active sensing contributes very, very much to our inability to do, better weather models. Right. So the airplane network is a possibility. Unfortunately, there does not seem to be much infrastructure even now to harness this network, at least in the places that we are flying. Right. As I said, there have been some basic efforts, but it's not clear how useful they have been, and it's more of an infrastructure and engineering, and the will of airlines to be part of that ecosystem. That's more of a socio-political problem than technical problem at this point. So hopefully with some of these kind of machine learning techniques, you can circumvent some of those barriers. But again, nothing beats than having active sensing.
One Carlberg actually asked something in a different context, but talking about creative thinking and solving problems. So do we ask the right questions? My question as well here, in the sense that you brought up the example of a bird in the beginning, right?
Yeah.
So you said there's that fascinating thing that birds can fly hundreds of miles seamlessly, nearly. So we perceive it as well. So instead of trying to figure out how we can measure everything in the area and in the air, is there a way to think about how can birds solve the problem?
Yeah, no, absolutely.
Because we don't have the sensors around them, right?
Absolutely. And I think this is that's one of the fascinating aspects, right? It's mysterious, and it inspires and mystifies me all the time. One of the things also I realized that these guys are not going on a fixed flight plan. They are free. They are free will. They can sense information up there and make a change on the spot.
Yeah.
And we don't do that, and that's what the part 2 is about. So it's a great segue into the second, right? Instead of flight plans, what if we had flight policies? And it makes regulators a little bit uncomfortable, the idea of flight policies versus plans. A plan says that it's a deterministic thing that I'm going to do. I'm going to go and follow this A, B, and C route, and sure, if I change, I'll let you know, right? But flight policy is that I have a policy. I'm going to act on the information I see at that time on my own, right? And the birds don't have to do that, but the airplanes will have to do that. So there's an interesting thing. So again, let's think, at least think, theoretically what's possible. And then we can chat about some of the implications of regulation, because this is, to be honest, part 2 is great. I do see a lot of possibilities, but a big challenge is socio-economic, political, and figuring out, our regulators to accept some of this thing, right? Yeah. Whereas part 1, I think we can do it right now, right? We can generate these weather maps, make it available for public, and, like NOAA versus ECMWF versus GFS. All these are anyway predictions. Why use one prediction over another, right? At least this is being informed with the real, the real sensors. But part 2 is more ambitious. It's more out there, and but something at least we should talk about. Yeah. All right.
So 2 questions from Pavel.
Yeah.
Compared to what you said before. So what is GPR aloft?
Oh, GPR aloft. Okay, that's let me just go back. So so NOAA is basically a comparison. It's what weather prediction agency is saying. That's what the winds are going to do. GPR aloft plus aircraft is basically using the Gaussian process prior, right, and using the aircraft information to improve it. The GPR aloft is basically an interpolation scheme. It operates on top of the NOAA weather and basically uses the spatial smoothness prior to say that nearby locations should have similar things. And it's kind of showing that this is not a great prior, because because of the various land features, various geographic features, the wind field is not necessarily very smooth, especially at the lower altitudes. At the high altitudes, probably it is, and even then there might be some discontinuities. But utilizing aircraft information allows us to break that smoothness restriction, right? So it's more of a comparison, making sure that our methods that we are looking at is correct.
And here's another question: where's machine learning used in the wind field prediction? Is it a time series prediction or simply interpolation?
So right now, this is doing interpolation, spatial interpolation. Right, and the reason we are not doing time series interpolation, because even the weather models that are spit out by our current simulation models, they are done, at least in the aviation case, they come out every 6 hours, right? So 6 hours is enough time that even if you have like local spatially interpolated wind fields that are better, they'll still have impact. But yes, you want to do temporal, but right now this is not temporal, this is spatial.
Okay, thank you.
Okay. All right. So next, think about routing. So as I said, right, imagine you are a bird and you're flying through a wind field. Very likely you will sense things and make a decision. And that we want the similar capability in an aircraft as well. So we are going to look at the robotics literature for that, right? And we are going to use something called receding horizon control. So what does this mean? So imagine that you're a robot. A robot has a choice of trajectories it can take. It can go straight, it can go left, it can go right. Let's start with 3. But in reality, there are a bunch of things it can do, right? And every time it does it, right? It's, for instance, in this case, it decides to take this green trajectory. You sense information. You sense information just along that trajectory, right? And then you come to the next spot. Now you have a little bit more information, right? You have information on what the winds were doing according to what you did last. And you can incorporate that information in your decision making, and you can take the next step, right? So this is what the receding horizon control is. So basically, you are collecting information, and based on the information collecting, you are moving forward, right? Very straightforward. This is a very popular algorithm. A lot of roboticists use, and people who are familiar with robotics probably know this algorithm. So he said, all right, let's just use this algorithm, right? So here's what's going to happen, right? We define something called a reward function. So imagine you have an airplane. We have 2 choices, left and right, right? And your reward is a function of 2 things. One is how long you take to cover the trajectory that you decide upon, plus some kind of estimate of how long it will take you to the goal. That's your reward function, right? And basically, what you do is you formulate this problem as a multi-armed bandit problem. So what I mean by that, like, if you're familiar with multi-armed bandit, you have a bunch of choices and you pull an arm and you get a reward. And based on your reward, you change your policy and keep going. So here also, every robot at every instance, he has multiple choices, multiple trajectories that they can take. And as you choose a trajectory, you see a reward or a proxy to a reward in this case, right? Which is your time, right? And based on that, you keep the statistics of how things evolved, and you make your next decisions, right? And in this case, we are using an algorithm called UCB replanning. So what's happening is that your choice of trajectories, each of these things, have a real number associated as a reward. So what you do, you associate a distribution, which we are called upper confidence bound replanning, right? And you keep these statistics, and you use a measure which is a combination of your expected reward that you're going to see plus some variance around it, right? And people, familiar with UCB literature, basically know that this is a very standard trick. Like, our innovation here is taking the UCB algorithm and putting it over this use case, right? So we are not innovating in an algorithmic space. We are using an existing algorithm and just applying to the problem. Right. There are 2 components, as I said. Let me see if I have that thing. No, we don't have the mathematical version of it, but it is a combination of a mean and average statistics that you're carrying, plus the variances that you're seeing, right? And the way you make decisions, it tries to optimally trade off between maximizing your reward and also ensuring enough exploration, so that you get enough information to make appropriate decisions as well. Like, if you were just exploiting all the time, you might miss some information that's useful. So this is trading off between exploration and exploitation in a principled manner that a lot of folks have before me have worked upon, and they have some nice theoretical results, right? So again, here are a few simulation experiments. Again, this is something that you can only do in simulation. I tried actually implementing this algorithm on my own aircraft. As I said, as I said, I'm an avid aviator as well, and over the short distances, this has limited settings, but over long distances is where it shines. So for instance, when you look, planning from Seattle to Miami, right, the kind of deviations that you'll see are quite large, almost up to 200 to 300 miles. Whereas when you are looking at, small distances, that deviations is not that much, right? So, this kind of scheme will be extremely useful for long haul flights, the transcontinental, transatlantic, the polar flights. And as I already mentioned, right, we've already seen some anecdotal evidence of this happening where flight planners actively working through come up with better routing. But this is an automatic algorithm. This is basically is a policy. This is not a plan. So consequently, you got to be thinking about regulation as well, right? So yeah, so I think those are the two ideas, Stephen, that I think we've been thinking about, right? There are few things as I talk about this, right? I do believe that it's possible to significantly reduce flight time very consistently by better wind forecast and better routing. As I said, incorporating the new wind forecast is technically straightforward. You on your laptop can do it right now. It's not that different, right? The key challenge is, however, is convincing your airline partners, the government bodies, and everyone to actually incorporate that in your workflow, right? The landscape is very fragmented, and of course you got to make sure that you have the SLAs, the engineering guarantees, and things like those. I'm a technologist, so I have a technical solution, but a lot of legwork needs to happen before this becomes reality. This becomes a standard process in the airline workflow, right? Which is a lot of a lot of evangelization and a lot of pushing is needed, right? The second thing is the newer routing paradigm is tougher, as I said, right? This is flight policy, it's not a flight plan. And one thing that people in aviation really like is determinism, their ability to basically stay on track. That's how all the metrics are defined, right? If we are track or not track. And if you are proposing something which is a policy, we need newer constructs, newer understanding, newer workflows to incorporate those, right? And of course, regulatory approvals and certifications are appropriately needed, because this is now operating on a vehicle, as opposed to just a wind map that anyone can utilize as information, right? So this is a harder thing to do. I do believe that this kind of routing paradigm will be very key right now, especially in eVTOLs and UAVs, which are using battery as their primary propulsion source. And as we know that the batteries are not very efficient right now, their power density is much less compared to the regular fuel. So, right now, like a 30-minute flight that's possible, if you use the winds appropriately, might be able to sustain for quite longer than what these batteries can provide, for instance, right? So I think there is a lot of potential there. But as I said, there are some challenges. But one thing, this is there's not many people think about, especially technologists, but this is something called a Givon's paradox, that more efficiency might lead to more consumption. And this is nothing to do with technology. This is about society, right? Imagine you are saving 2 hours of fuel on every flight, and that allows you to scale your operations up. Now, instead of having one daily flight between New York and San Francisco, all this savings, all this efficiency led to 3 flights a day. So it might, technologically, it might show us some way, but there might be other socio-economic factors that might lead to a worst case scenario, and that's something we should be mindful of. It's called Givon's paradox, and one of my collaborators, John Platt, was very kind to point this out to me. So it's an interesting thing. As I said, this is a very difficult problem. As a technologist, we can make some inroads, but I do realize that there are many different aspects of things that are affecting it. So yeah, Stephen, that's all the material I had.
That's fantastic. I mean, we have a lot of questions. So,
yeah.
One thing, can you just show the algorithm slide once more?
So which one? The
the slide with the formula.
the formula, the Gaussian process one, or this one?
Let me check. Nafjot, I allowed you to speak up. What kind of slide was it? Do you remember? Can you hear us? I guess you can hear us. You can also speak now because you're allowed to speak now. I thought it was the part where you show the mathematical formula.
Oh, I see. The Gaussian process one. Okay. Okay.
Totally walking back.
Okay. Yeah, there you go. Okay. So yeah, I can explain this graphical model. So here's what's happening. You have a wind field W, which is latent, which is the true wind happening on the globe between 3,000 feet and 60,000 feet, right? It's a wind vector. It's a random variable that represents that wind vector, right?
Okay.
And you have something called a Gaussian process prior over it. So S is basically these, some encoding of latitudes and longitudes. So imagine there's a grid sitting on top of it. So that's what S represents. So we know the longitude, latitude, and altitude of this.
Yeah.
There is a Gaussian process prior, which is saying that wind at locations which are nearby each other should be similar. It's a smoothness prior. It's a Gaussian process smoothness prior. It's a very standard textbook now. At that time, people were still working on this thing, right? But this is smoothness prior. So now the question is, what is this? Our basic inference problem is, what is that wind field, right? So we have two sources of information. The first source of information is, observation from wind stations. There are weather agencies that have, instrumented, various sensors. So you can, in this case, I think we are using wind aloft information, which is saying that at every geographical coordinate, what kind of winds are you seeing? And we treat them as observations. So the blue node means that, this is the data we have. And you can imagine there is a relationship between the actual wind. This observation and the actual wind is connected via noisy process. And in this case, the noise can be, a simple, a normal distributed noise, but there is some noise there. What you observe is a noisier version of the truth, of the reality, right? Mm-hmm. So that's what this link represents. On the other hand, you also have the aircraft. For the aircraft are not directly measuring the winds. They're not measuring the local winds, which is we call TI. But instead, what they are measuring, so because they're not measuring TI, that's why it's unshaded. This is basically, we don't know. Sure, it's experiencing wind, but there is no sensing of happening there. What we have sensors, we have GPS, right? So we know what is the velocity in the longitude and longitude. There's a vector, velocity vector. We know, I've factored into X and Y direction. But what we have basically the velocities, and this velocities that you're seeing is related to the local wind this airplane is experiencing via the triangle that we talked about, right? The vector triangle, and that's encoded as a potential function here.
Yeah.
Right. And of course, this is the same relationship here. And so what we got this information, the wind station observations, and we have the aircraft velocities. And our Bayesian inference problem now is, what is the posterior distribution on the wind field given what you've seen at the wind station and what you've seen across all the aircrafts in the sky? That's a numerical optimization problem. We basically use something called Laplace approximation, because this is an untractable graph for closed form inference. You use some numerical techniques, which are again very standard in the Bayesian inference literature, to come up with what that W is, right? The next generation of this is very simple. Actually, you just throw TI, W, VI, and all this thing into a neural network, and then you try to predict it, right? But this is from 2014, where that was still kind of in style. But you can do it with any other machine learning technique as well, as long as you can encode all this physical phenomena, that observations or intuitions in it.
Yeah, interesting. So let's sum it up a little bit, since we're talking about how to put in environmental aspects into aviation and to make aviation more environmental friendly in some ways. And you focused on thinking about how we can use natural capacities in a better way. In some ways, right? Yeah. We have some questions which focus a little bit on different areas, and I just wonder what your opinion would be here, or your knowledge is. Do you know what kind of companies are working on more environmentally friendly flight engines like Rolls-Royce and GE? Or
Yeah, absolutely. I think this is like electric aviation is big.
yeah,
Like electric aviation is big, and even in my in my aviation circles, there's always a talk of it. I am located at a place which is the hotbed of electric aviations coming through.
oh yeah,
So, we have a lot of startups around here that are looking to provide electric powertrain for different form factors. Companies building these power plants, actually airlines that are actually trying this power plants out. Not very far from here, Vancouver. So Seattle is there is a seaplane flight from Seattle to Vancouver. It's one of those places in the world where transportation by sea airplane is actually common, much more common than the rest. And there are outfits here who are trying this on seaplanes. And you can imagine, like, seaplane is not the best of the form factors because it's so draggy and all that. But the great thing about seaplane is because it's flying mostly over water. Even if you lose a battery, you have a very nice way to land without creating catastrophic thing. But also the flight times for many of these seaplane flights are fairly small. They are over 50 to 100-mile range, where we believe that the electric aviations can actually support these kinds of things. On the bigger form factor general aviation, as well as other electric aviations, I'm familiar with those. No, I mean, I'm nowhere near an expert in those things. I know that folks are working on it, and I'm inspired, and I'm looking forward to see the advances. The biggest problem really is the battery density, to be honest. Unlike a Tesla car, right, which can actually carry the battery itself, with aviation we have to be very weight conscious, right? And so consequently, unless the battery density goes up, it'll be a while before this thing gets impacted, in my opinion. Again, I'm not privy to the advances in the battery density that are happening, but that's one of the biggest things that needs to happen. I do think that we have the motors, we do have efficient engines, right? But the battery density has to go up.
Yeah. Okay. I mean, since you're flying yourself, you have even more practical experience.
Yeah. Absolutely. So for instance, right, in the airplane that I have, I can go nonstop to San Francisco in 3.5 hours, right? And this is with a gas engine, and the efficiencies that I'm getting, they are at par with what the Prius would give me. Right, and it's mostly because, of course, I'm going straight line and things like those, right? So in terms of efficiency, I think there are still ways to actually harness the gas powered airplanes as well. But the fact is that there exists no airplane that will take me nonstop to Seattle to San Francisco. I mean, I will have to very much make multiple stops, and each stop, again, there is an expense. The expense is in taking off and landing. Yeah. That's where the bottleneck is. In aviation, right, the delays are happening at the terminal areas. They're not happening at the cruise. Once you're in the air, you're just going, right? But it's the delay on the terminal areas. So if I have to stop every hour, that is going to increase inefficiency at a different level. Yeah,
sure. Yeah, makes sense. Interesting. Can you stop screen sharing for a second, Ashish?
Say that again, sorry?
You stop screen share for a
second. Oh yeah, I will, yes.
Frank, you asked about the role of AI in developing lighter and stronger materials used to build aircrafts. I'm not really sure if Ashish can answer something like that, but a quick hint to something which I usually show in some cases. It's called generative design. It's an AI method as well.
Yeah.
And the interesting part is this kind of design you can see, which is actually in an airplane. It's a separating wall. And you can see the construction here, which looks pretty crazy, right?
Yeah,
This
yeah, yeah.
part here has been designed by an AI. Yeah, it was not by an engineer.
Engineer, yeah.
And this is fascinating because, of course, so we put in every kind of formula, optimizing material, optimizing weight, optimizing
Yeah,
the static here. So this is something which can be done with AI.
yeah.
So this
With AI, that's
great.
great. Yeah, no, Stephen. Yes, this is amazing because I do believe that AI can do a lot in manufacturing. This project with EPFL that we announced, like a month ago, with Pascal Four's lab at EPFL is actually
Search for
looking.
design,
Hold
generative
on,
design.
just keep it quiet. So, okay.
Yeah, yeah. It's looking at joint controller and wing design. I know someone
Yes,
posted the paraglider work. So we are also looking into form factors as soaring,
yes,
like
cool.
autonomous soaring, and instead of just thinking about the policy or the algorithmic aspects, we are thinking about how to jointly design policy and the airframe together.
Yes,
Right now, it's a sequential process. Right now, you have an airframe, then you have an autopilot that comes out.
yes,
And I do believe there are inefficiencies there.
yeah,
So we've been looking at simulations, differentiable simulations specifically, where you could possibly optimize for every single piece in the pipeline, all the way from manufacturing to a policy. So it's great to see your example as well, because it fits very well into some of these aspirational directions we want to pursue.
yeah. I just thought also for Jarmis code. So for everyone here, just in the call as well, the label is generative design. That's the name for it.
Yeah,
To look it up, and this is especially for trying to build up things in a different way. We had some similar discussions, and with a bridge in Amsterdam.
yeah,
The previous talk, I think 2 years ago or so, which was also going into that direction, using robotics and trying to use machine learning and AI to build a model for a bridge. And this was entirely built by robots and by e-printing, also and those crazy stuff. But coming back to what you just said, one of the questions was also, what are examples of light policies you wish to see?
yeah. No, absolutely. So there are few things that we got to do right now. Our flight plans are linear,
Yes.
right? Linear. So I think the next logical step is actually going from linear to nonlinear.
Uh-huh.
So when I'm I should be able to follow contours. This is already happening. When you have a direct flight to a waypoint to a large geographical distances, you are actually following the great circle route usually, and which is actually not linear. You're changing your direction every single moment. So it's happening there. But our ability to circumvent around areas might be very, very useful, right? It'll give us at least the initial boost without stressing out the regulatory mechanism. Even that step will be very useful. The second thing is, when the ATC does this already, right? When you are basically in an area where there's no air traffic control, they would tell you, like, altitude, your description, your discretion, right? They'll say, all right, I given you 5,000 feet, you can be flying wherever you want. Right, and that's great, but formalizing this, having an autopilot automatically choose it will be very useful.
Yeah.
Because when we are doing these decisions by ourselves, we are discretizing, and in this discretization some of the efficiency might be lost.
Yeah.
So I think at least to start with, in the cruise flight, this bulk zone or a pipe that you get assigned, that all right, you can actually do whatever you want in this thing, will be very useful to start with.
Interesting. Absolutely interesting. We have to last questions basically as well. So Frank, again, so you asked more in direction of biofuel, e-fuels, right? This is indeed another aspect of thinking about how to make aviation more environmental friendly. So far, I cannot see, Ashish, you can please correct me if I'm wrong. I do not know of AI being part of that development process in that context. Maybe in the chemistry, I don't know. The
Chemistry.
only thing I
Yeah.
can think of maybe in still calculating efficiency in flying or so. And
Yeah. So yeah. No, I think it's a great question. I think AI can help. Again, I'm not in those discussions, so I'm not very privy to any of the AI that might be used. But I'll mention this to you. Like long time ago, um, you know, I mean, even now, people are looking at various materials for things like fuel cells,
yes.
right? And our ability to identify right kind of material, right kind of semiconductors is very important. So what AI can help, and I think people are looking at it again. This is me now, speculating more than giving you answers, is our ability to do experimental design, as in use the data from the existing experiments you might have done with materials,
Mm.
and then propose a list of candidate materials that might be most promising.
Yeah.
Right. So there are potentials there, but again, as I said, I'm not very involved in that effort, but I do believe that this is something that could be useful.
Yeah. Yeah. We have one question regarding the understanding again. So from Pavel, what is scale of smoothing wind field? Would
Yeah.
that be able to preserve relatively narrow features like jet streams?
Jet streams. Yeah, it's a great question. I think this whole. So again, the smoothness prior, the Gaussian process smoothness prior, has something called a kernel function. So the kernel function is how do you define the smoothness, right? So often a lot of people use what they call a radial basis function, which is least square divided by a scale length. So larger the scale length, the smoother the field is. Smaller the scale length, more less smooth the things are, right? So in our case, we had to do hyperparameter optimization. So what your kernel function is, a kernel function is a linear combination of multiple kernel functions. And so these are similarities in your latitudes and longitudes and altitudes, and you are scaling them appropriately. And what is that scale? That scale basically came from empirical, what we call evidence maximization, or maximizing marginalized likelihood. Now, off top of my head, I don't know what exactly it was, but I think it was a scale of like 0.25 miles or something like that, which I thought was okay to model the jet streams.
Yeah.
So again, just to give you a sense, we do have control over these trade-offs between how strong this prior is, because there's another noise parameter between the observations and the GP prior, and you can attenuate that as well. So there are multiple moving knobs, and in this case, all these knobs are done via empirical evidence.
Mm. Okay. And there was a follow-up question I actually missed to ask you. So this is good as well.
Yeah.
Frank is asking again, do I understand it correctly that non-linear flight policies means that passengers need to be more flexible regarding when they can fly?
No, it's no. It's not about when they can fly. It's about once you are in the air. So here's the go. Imagine you're going from New York to London, right? Once you take off, you know that you're going to take off from New York and you're going to land in London.
Yes.
So what's happening in between? That's the captain's description and your pilots and ATCs, and that's what we're talking about. So you as a passenger, you are not paying. It's you are still flying at the same time, but it's the cruise part of the flight. Right? That's where instead of you just going direct to London or going direct via established air routes, usually there are established air routes. A lot of times you will just follow, but having some flexibility to go around it. Right now, it's at the discretion of ATC, but if it was scaled up, it will be very useful.
Yeah, cool. I think so. I think awesome. We had a lot of questions that basically, I think it's also the session with the most questions ever. So
That's great to hear. I hope, I hope this, inspires and show that we can actually, make a difference, at least from technology point of view. At least start.
I think absolutely it's a good thing that you're working on such things, because we will still fly, and we need to be more efficient, more taking care of the environment and of this planet in some ways.
Yeah, great. Thank you for having me here. It was great.
I should say thank you again for just taking the time today, answering all the questions we had, being so patient with us. And I can just say that you are also on LinkedIn, of course, which is one way where we actually connected. And so everyone who tries to follow up on what you're doing and your work, just connect. I think it could be a good idea. And as always, since we are just recording the sessions, don't forget it will be up probably in 2 or 3 days. You will get the information via the AI Suisse meetup platform. And I will also put the PDF with the presentation up there from Ashish. And yeah, thanks for joining us, and really thank you again for taking the time and being part of it.
Well, thank you. And yeah, please stay in touch.
Yeah, have a nice evening, have a nice day, morning, whatever time it is. And I say goodbye. Goodbye.
Bye.